Let's move to the last speaker of the first part of this session. The speaker is Professor Vitalyi Gusev. Professor Vitalyi Gusev is currently a professor at Leman's University. His most recent research has focused on applications of time domain, Brillouin scanning for nanoscale imaging on nonlinear laser, ultrasonics of granular media, and non-destructive testing and evolution of nanomaterials and nanostructures. It has more than 350 publications, and his H index is 51 according to Google Scholar. Wow, wonderful. The title of his presentation is Applications of Time Domain Brillouin Scattering for Nanoscale Imaging. So welcome, Professor Gusev.
Well, thank you one more time, for your kind presentation. So I will describe you the results obtained in the Le Mans University in France on the topic which is called Applications of Time Domain Brillouin Scattering for Nanoscale Imaging. So it is already nearly 40 years when Humphrey Maris from Brown University introduced in the research what it was called picosecond laser ultrasonics. The point was that using femtosecond laser pump probe technique and measuring, exciting the material and measuring transient reflectivity, it was possible to monitor the propagation of the acoustic pulses inside thin films. Just imagine that the pump laser is absorbed near the surface, and then due to thermal expansion, the acoustical pulse is launched inside the film, and it could propagate, and be reflected, at the interfaces. So there are two typical situations. First of them, if, the film is opaque for the probe light. And probe light, these are also femtosecond laser pulses, which are coming with some delay on the surface, right? And so if the sample is opaque, the acoustical pulse could be detected only when it comes close to the surface in the skin depth. And in this case, we see like typical ultrasonic echoes, This pulse comes with the 2 times propagation in the film, then the next echo, and so on. But the pulses are picosecond, and the length of the pulses are nanometers, which are useful for nanoscale imaging. At the same time, if the transparent material, if the film is transparent, the signal changes drastically, We see all the time, nearly all the time, this sort of a Brillouin oscillation at some frequency when the pulse is in any position inside the film, and the arrival of the pulse on the surface or on the interface is could be understood from the change in the phase and the amplitude of these oscillations, which are called Brillouin oscillations. So I will explain now why they are called Brillouin oscillation. First of all, it's just because the frequency corresponds to what we call Brillouin frequency shift, in the ordinary frequency domain Brillouin scattering, when we detect light scattering from the thermal phonons. In coherent acoustics, in time domain Brillouin scattering, the situation is the same. This is still photon-phonon interaction, but how it happens? So we have the pump laser light, imagine absorbed near the surface, acoustic pulse starts to propagate inside, and the probe light, it is delayed probe light. with time, yeah? It is reflected on the interface, strong reflection, and then penetrates inside the transparent material, and just a bit, yeah, tiny scattering by the perturbation of the refractive index, which is introduced by the acoustical strain pulse. And so then on the photodetector, the strong and the weak rays are interfering. And we see with you the maximum, minimum when they interfere constructively or destructively. And this is continuously changing because, you know, the phase delay between two laser pulses is continuously changing. Otherwise, it could be understood as a Doppler effect. Yeah, actually, when the probe light is scattered by this nearly transparent acoustical mirror, yeah, moving mirror, it exhibits the phase, it exhibits the frequency shift, Doppler frequency shift, and then these two light beams, they are different frequencies, and the different frequencies is recovered by measuring the intensity, interferometric measuring of intensity by the photodetector. So all these could be, you know, supported by theoretical formulas. So the most important is, if you look, this is a formula for electrical field reflectivity. We understand, you know, if you like mathematical formulations, that the signal is a Laplace transform of the strain distribution inside the material. Yeah, it's Laplace transform because K here for the optical probe, it's a complex wave number. So Laplace transform with a complex wave number. And immediately, if you transfer here from to the integration in the moving coordinate frame with the sound velocity, immediately this, you know, Brillouin oscillation, you know, this exponential appears at Brillouin frequency. And also, if this special integral you transfer from the real space in the reciprocal space of the wave vectors, it immediately seen from here, from the denominator, that there are profitable conditions for Brillouin scattering, and they correspond, in our case here, to the backward Brillouin scattering. Yeah. And the final, third way to understand the Brillouin oscillation is to calculate the intensity reflectivity at the photodetector, the changes, and the result is that these changes are proportional to, so the integral over the volume where the acoustical strain exists, and there is some sensitivity function which is produced by the incident and scattered probe light. Yeah, so it is just sinusoidal with some decay and phase shifted. So blue is the sensitivity function. And in most of current experimental situation, the length of the acoustical pulse, here depicted in red, yeah, the length, it is on the 10 nanometer scale or less or a bit more, but the Brillouin wavelength acoustical, which is just one period of oscillation here, it's difficult to achieve less than 100. And so you understand that when this pulse is, you know, going through the material, it just, you know, translate to us, yeah, give us opportunity to imaging this sensitivity function. And like, you know, 5 years after introducing picosecond laser ultrasonics, Humphrey Maris suggested that if we are able to measure the frequency of the Brillouin oscillation, let us say of one period of Brillouin oscillation, then what we know, we know with you the product of the acoustical velocity and refractive index, yeah, in the position, you know, related to the acoustical pulse. Yeah, and this provides opportunity to imaging of inhomogeneous material. So it was 89, yeah. Amazingly, but only 20 years later, the first experiments were conducted, and they were conducted in France and the United States. In Le Mans University, we did the depth profiling of nanoporous low K film, yeah, of submicrometer thickness, yeah, curing, yeah. So you see that it is inhomogeneous in depth. It is inhomogeneous in depth. So the pump excites the acoustical pulse, and this is depicted by green, and this green pulse, propagates inside the material and could be reflected, and the probe light, is scattered in the overlap of the probe with this moving acoustic pulse. And so we get, when time is increasing, we get information from different position inside the volume. Here is the signal, yeah, then when only as Brillouin oscillation is revealed here, this is the Brillouin oscillation, and the Fourier transform with the short time window describes that Brillouin frequency, increases from left to right. Yeah, inside, and the material is highly inhomogeneous. Yeah, and when the pulse is going left, right, right, left, the frequency is increasing, decreasing, increasing. So inhomogeneity is due to curing with the application of the UV light, which penetration depth is comparable to the thin filterness. And even in the best case, material is still inhomogeneous. What is important is that by making experiments at several angles of probe light, yeah, we measure several dependencies of Brillouin frequency on time, and this provides opportunity to disentangle information on refractive index and sound velocity. And so we see how inhomogeneous are both of them, and also the interaction coefficient. So this experiment provided the resolution of 40 nanometers, which was still limited not by the length of the pulse, but our signal processing. And this is just more than 3 times smaller than the length of the Brillouin oscillation. And at the same year, in the United States, there was conducted imaging of the damage produced in gallium arsenide by ion irradiation. Yeah? So this is the Brillouin oscillation in red in the intact material, so unirradiated by ions. And you see just the decay of the Brillouin oscillation caused by the attenuation of probe light and the acoustical waves. But in irradiated material, we see that the amplitude of Brillouin oscillation is diminished at some particular time scale, which corresponds to like 1 micrometer depth from the surface. And the explanation of these results that ion radiation were not changing refractive index or sound velocity because the frequency is the same in both experiments, but the interaction constant, photoelastic constant, became inhomogeneously distributed inside the material. And nowadays, let us say 15 years after the first experiments, there are applications of time domain Brillouin scattering in different research directions. I will describe to you some of them. And current situation that this TDBS imaging, when we measure the local Brillouin frequency, yeah, in the position of the propagating nanometer scale acoustical pulse, yeah, it is in depth. Depth resolution is controlled by signal processing and is from 10 to hundreds of nanometers. Lateral resolution is controlled by our focusing by diffraction limit and is about micrometers. And what is important, this technique has a large, depth of imaging, up to tens of micrometers. And this imaging depth could be achieved without moving laser focus or without moving the sample. I will explain our experiments and advantages of this time domain Brillouin scattering for imaging of polycrystalline material, and especially at high pressures. So if you look how the frequency domain Brillouin scattering works, so we shine, unfocused laser light in the transparent sample compressed between two diamonds, and the scattering signal comes from the volume filled by the probe light, So it's actually like huge volume, because the dimensions of the samples are tens of micrometers. Then if you want to make FDBS, frequency domain Brillouin scattering, but microscopy, you could focus better the probe light, but still this dimension, the dimension of the sample in the diamond anvil cell is fixed. So you could gain 2 orders of magnitude, but not more. What is important that in time domain Brillouin scattering, it's not important that the light could penetrate the complete sample, because the scattering volume is overlap, of the probe light and the acoustical pulse, which is depicted here by white, And so 2 other orders of magnitude could be gained. And this is important because to understand the elastic constant of materials at high pressure, it is desirable to measure, separately different grains, And then when the grains are multiple, we finally choose the maximum velocity and minimum velocity, and then through the theory, we could extract elastic constants. But in reality, if the grains are too small, we have here, for example, the acoustical pulse is limited by diffraction limit, this dimension, we have a sort of averaging. So we don't have access, to precise constant, but still TDBS provides better access than frequency domain Brillouin scattering, because the scattering volume is significantly diminished. And so here are the first results on the imaging of water ice 10 at 84 GPa pressure, in this configuration. And here are the results of 1D experiments. You see that Brillouin oscillation is, strongly changing with time, both the frequency, the amplitude, and it's in a single point. And the Fourier transform, with moving window, provides you the profile of the Brillouin frequency, predicting there is sort of layering in this direction of water ice 10. And then we conducted the scan in one of the possible directions. And so we are scanning, changing the position of the palm probe, and this layering was reproduced. So here is the map of, if you want, of the texture of water ice 10 at huge pressure, and different colors, different frequencies corresponds to different orientation of the crystallites in different regions. Later, we started to apply more powerful system for fast acquisition of the signals. These are 2 lasers with a bit shifted, repetition frequency of the pulses, which actually replaces the scanning optical delay line, So the system is much faster, and it is possible to do 2D and 3D imaging. And also we did the imaging, inside the individual grains, like in this type of the situation. Here are 2-dimensional slices when our pulses were, and the surface area is 40 to 40 micrometers square at increasing depth. And you could see that the interfaces between the grains are moving. And here, the most dark grain is diminishing with depth in its size. So it's like crystal. This crystallite is disappearing with depth. and combining the slices, it was possible to reproduce 3D image of the water ice. Also, very recently, we started to apply also shear acoustical pulses for time domain Brillouin scattering. They are could be launched, inside the transparent material from the metallic generator if the material is elastically anisotropic, what is the case of the ices. And in Brillouin scattering, if you make the Fourier in the time domain, there will be beating between shear and longitudinal waves, and in the frequency domain, we have different peaks. And you could appreciate that the image with the longitudinal waves is very different from what we could obtain with the shear waves. So analysis demonstrates that shear waves are very profitable for imaging of the crystals, or polycrystals. Why? Because the velocity anisotropy of the velocity for the shear waves is much stronger than for the longitudinal. Here are the presentation of the slowness curves, and you could see this, And so shear waves are much more modified when transforming at even weakly inclined, weakly disoriented grain. Here is the example of the imaging with longitudinal wave, and the two grains which are not distinguishable by longitudinal are distinguishable by shear, here fast shear wave. And here two grains undistinguishable by quasi-longitudinal are distinguishable by slow shear wave. And here how it looks like in 3D, in 3D. So the grain boundaries, they are mostly obtained now by profilometry. It means when the acoustical pulse comes to the interface, and so this process is probed by the laser light, and there is a transmission and reflection of the acoustical pulses. So the signal changes significantly, and so you could identify the point. And so by doing the experiments, scan, you will find the position of the interface, in different lateral position, and then you can put the interface inclination. However, what is important that it could be done differently, and inclination could be obtained in the single point, while because the signal from, for example, transmitted acoustical pulse, it is strongly dependent on the inclination of the interfaces. You could see here that with increasing inclination angle, the duration of the Brillouin scattering signal is drastically diminished. And so it is possible to obtain locally the inclination of the interface between two grains. We appreciated this recently in experiments which were devoted to imaging of the destruction of the single crystal by application of non-hydrostatic loading. So initially we took a single plate, lithium niobate plate, single crystal, deposited titanium transducer for launching coherent acoustical pulses, and at room temperature in any point of the sample, making the line scan, you see the TDBS signals are all the same. The frequency doesn't depend on the position. And so perfect plate. And then at 10 GPa, it was possible to see optically, just in microscope, that the rupture, the damage of the sample was taken place. And immediately in each point of the experiment, I mean that the plate was loaded in the diamond anvils and the pressure was increased, you see that TDBS signals are very different, very different. You could see not only Brillouin oscillation, but also the arrival of the individual acoustical pulses, And also you could see that the arrival of the acoustical pulses on the rear surface, of the plate is different. So here is the image of the arrival times, and here is the image of the average Brillouin frequencies over the propagation depth. So both are, indications of the destruction of the sample and strong homogeneity. What is important is that all these interesting shapes of the signals could be understood by theoretical developments, which take into account that we have Brillouin scattering in the beams. We have here, we have green probe beams, and red beams correspond to the propagation acoustical pulse, and we need to take into account that the damage of the generator and the probe light, and so the acoustical pulses are emitted normally to the generator and not linearly to the probe. This influences on the brilliant interaction intensity, but also you see that we need to take into account the overlap of the probe light and the acoustical beam. Here, for example, if we diminish, both diameters of the beams, you could see that near the rear surface, they are not overlapping anymore. And this could be explanation why in some position, we don't see the arrivals of the acoustical pulses crossing once the plate. I'm coming close to the end of my presentation. I want to mention here that the TDBS, time domain Brillouin scattering, could be used also and is using for imaging transient processes, right? So transient processes. First of all, these were not changes in time of the material. We were imaging the changes in time of the propagating acoustical pulse. The easiest to understand the example with the nonlinear acoustical pulse, when in the acoustic pulse there is a weak shock front, which when pulse is propagating, acoustical shock front is attenuated and its velocity also is changing with its amplitude. And what's happening is that the probe light is mostly scattered by this front. So front produces the reflecting mirror. And then, when the velocity of the front is diminishing, the Brillouin frequency is diminishing. It is also possible to image with TDBS the focusing of initially micrometer side, acoustical beam inside the optical fiber. It could be focused to below 100 nanometers diameter spots. And the most recent results, initially, we were able to demonstrate that the grain boundaries between the I6 and I7, which are coexisting in water ices around 2.1 GPa. So these interfaces are slowly moving with time. So we were doing, let us say, profilometry. We were detecting the position of the interface, and we found that the interface was moving with the 30 picometers per second velocity. So this was indication of the transformation of I7 into I6. And recently we returned to low K materials, nanoporous. We took several samples which were, let us say, well-code, or under-code, non-code at all. And we conducted the TDBS experiments. So we observed that in general, our experiments, they are invasive. It means that the heating of the sample due to heating of the optoacoustic metallic transducer, but also due to possible two-photon absorption of probe and pump light, it could modify the material. And you see here, for example, the period of the Brillouin oscillation is diminishing with the time of imaging. Here it's just how with time the Brillouin frequency changes. And the similar phenomena were observed in important for industry situation. It's the epoxy interface of the epoxy with the metal film. So it was possible to observe in real time the curing of epoxy at room temperature, or increase the speed of curing at higher temperature. And we were able to see how the Brillouin oscillation frequency is increasing and how the attenuation of the acoustical wave is decreasing. This is also visible from time domain Brillouin scattering, which are time domain TDBS signals, which are becoming longer. The pulses penetrate deeper and deeper when the material becomes more and more rigid. So also we were able to observe that after our experiments, there are some residual, although small, but residual, modification of the epoxy. And so important was for us that after conducting additional experiments, we found the opportunity to do time domain Brillouin scattering experiments with the infrared pump and infrared probe. So there, the 2-photon absorption was included, and these experiments are completely invasive. So to give a just perspective for the time domain Brillouin scattering, the most important perspective from my point of view is to transfer from the measurement of the amplitude of the reflectivity to the measurement of both, of the amplitude and phase. Actually, what is important is to use, not ultra-fast reflectometry, but ultra-fast interferometry, because then if we detect the changes of the phase, with time, differentiation of the phase will produce us the local Brillouin frequency, with this local product of refractive index and sound velocity, without any need to apply sort of Fourier transform, which is always a sort of integration. So to go to the depth resolution controlled by the width or length of the acoustical pulse, we should go and construct ultra-fast interferometers for the application in TDBS. The other three, perspectives are common to all other imaging techniques. We need to find the ways to increase signal acquisition rate, for example, by multiplexing of the pump and probe channels, or also to improve signal processing and also signal interpretation, for example, by using physics-informed neural networks. When the huge base of, data is accumulated, it will be difficult to take the decisions ourselves. And of course, the most important is identification of important application, or let us say some unique applications, where only TDBS could be used. For example, in biomedical field, where TDBS applications are currently very strongly growing. So you could look that already the applications of TDBS are multiple. I described most of them, except, let us say, biological. And my final transparency is to acknowledge the contribution to our progress in our university of our collaborators from all over the world. You could see that geography is covering practically all the world. And in different years, many colleagues from my university, they also contributed to this project. And finally, in the last 5 years, the project was supported by the French National Research Agency. Well, thank you for your attention.
Okay, thank you, Professor Gusev. Thank you for a nice speech.